Answer these questions. You guys have these locked down now? Yep. All right. Okay, yes, of course they accelerate. Okay, now this one here, that might still be a little unclear. What that means is as the object is falling, does the acceleration stay 9.8 the whole time? It does. Okay, so that is uniform if it's a situation where we can neglect air resistance. All right, and you'll get to know what those situations are. Okay, they're usually short distances and, objects that are appropriate that air resistance won't matter that much. Okay, falling paper, obviously we got to deal with air resistance. Okay, do they accelerate at the same rate? Yes. Okay. Another way to say this is that the mass doesn't matter for the object. Okay? If you drop 1 kilogram here, 2 kilograms over here, they will hit at the same time. Okay, and then we got our value, negative 9.8. Okay? All right, now, part 1 of today, we dealt with this. We dealt with how fast something is going as time goes by. Part 2, we want to deal with this. All right, so up here, here's the variables we were dealing with. We got v, we got t, and we got one more. What is it? A, acceleration. Okay, now down here, we're going to throw delta x into the mix, or distance. All right, we're going to do some examples. Let's start with the graph of a falling object. This is straight from your lab. You should know how to draw this graph. Is it a curved line or a straight line? This is a curved line. Okay, something like that. All right, now if we're taking negatives into account, our graph would just look like that. In the lab, we just decided to drop negative signs and do this right here. Okay, some of you are on your phones and not listening. All right, now let's go to this. Okay, here's the equation we're going to use for figuring out where something is. Okay, we already know how to figure out how fast. Now we're trying to figure out where it is in space. Okay, delta x. Okay, now you've used this one already lots of times for like cars moving, trains going by, bikes, okay, anything in motion. Okay, we can use it like this for free fall. All right, now for a falling object, I don't care which one you write, okay? You can really use either one. You just have to know that you're plugging what in right here? Negative 9.8. Okay, so we're going to apply our same kinematic equations to free fall. Right here, are these changing equal increments? Yes, this would be your straight line velocity graph in your lab. Are these changing, the distance, are they changing equally? No, this is a dropped object, okay, and time going by. They don't change equally because we're using this equation over and over, and that equation has got a squared term in it. Time is squared. Okay, let's do some examples. Name that place. Anybody? Oh, who's been there? Some people been there? Oh, nice. Okay, road trip. All right, Yosemite. Okay, very cool national park. This is called El Capitan, and it's a big old cliff structure. Okay, in geology they will call it a monolith. All right, and it's really, really tall. Okay, I got some data for you. Well, first, people climb it. All right, and they look like tiny dots. If you stand right here, they look like tiny little dots. Sometimes people sleep on it because it takes so long to get to the top, you can't do it in one day. All right, and I actually have a friend, a crazy friend of mine has climbed this multiple times. Okay, and one time he's got this cool story. He was sleeping on here with his climbing buddy, and at night he heard like a whoosh sound go by, a couple whoosh sounds go by. And so he thought like rocks were falling or something like that. And so he looked down to see what was going on, and he saw 2 parachutes open up. So they were doing what they were base jumping like in that last video. And then they like packed their chutes up all discreetly and ran into the forest. 'Cause it's illegal. Okay, so here's some data for you. El Capitan is 3,000 feet tall. Okay, really big elevation here. Which is 915 meters. Okay, so let's say a little rock chipped off the top or something like that. Okay, and is falling down to the forest below. How much time would that take? Okay, solve that on your own. Okay, there's a space in your notes for you to do that. All right, I'm going to call randomly on one of you guys to give me the answer. Good, getting our calculators out. Okay, as we solve this, all right, couple things. First of all, this is the correct way to set it up. Listing what you know, all right? And as these problems get more complicated, I would draw a simple diagram. It's not hard, okay? I just drew a cliff, okay? The top, we're most of the time going to call 0. The bottom, we call the down direction negative, so I made my delta x negative. All right, now those negative signs are going to end up canceling here in a second. Okay, so 2 ways to do the math, and I don't care which way you do it. You can either plug numbers in and get time, or you can rearrange it so it says t equals. Okay, so here's the equation we're going to use. Okay, and I don't care which way you do your math. Either is great. Okay, I'm going to call you guys by your initials since this is going on YouTube. Okay, all right. C in the back, what do we get? Okay, do you guys agree? 13 and change? Okay, very nice. You said that so hesitantly, but look, it's right. Okay. All right, rounded it to 14 seconds. Okay, solving for t. Now, you did have to square root because it's a squared term. Okay, that's often forgot. So if you got a really big number, you're going to want to square that or square root that, and then you'll have the right answer. Okay. Let's do another one, a little closer to home. This is the Royal Gorge. Okay, it's got a cool bridge that goes across the river. So, and then that's what it looked like down from down at the bottom. All right, so let's say you're up there, all right, and you drop a penny off into the water. Okay? If you did that, could you time it with your phone or your watch? Okay, you could time it, and let's say you get a time of 8 seconds for the free fall. Okay, from this you can figure out how high the bridge is off the water. Kind of cool. Okay, so figure out that height. Okay, so if you're working this out for homework or something like that, okay, you're going to want to show this. Or if it's a test or quiz, definitely going to want to show your work. Okay, in fact, you get a point just for doing this. Something key, the initial velocity is 0. It is a dropped object. Okay, there's the acceleration, there's the time. We got to find delta x. Now this one's easier, right, because we don't have to rearrange. Okay, so here's our equation. Here's our numbers plugged in the right spots. Okay. Oh, absent, absent. Okay, h in the back, what do we get? Okay, very nice. We get 300 and change. Okay, I rounded mine to 314. Okay, if you plug it in like this, it will also come out negative, telling us the direction. Okay, now up here I have d's. I should probably replace these with delta x's, okay, because that means I'm giving directions as well. And if you're just asked for the height of it, you can drop the sign and just give a positive answer. Okay? All right, any questions on this one? Okay, what do we got? Okay. Yeah, like if you were going from this step to this step, could you put negative 4.9? Yeah, you could do that. It's just a little shortcut on your work, sure. Okay. All right, even closer to home. Where's this at? Okay, a student sent me this, and I thought it was going to be cool to analyze the physics for this. All right, so little video for you. He kept it nice and clean on there so I can play it in class. All right, and I think it's super cool that you can watch something like that, take some data on it. You knew I was going to get nerdy with it. Okay, if you look at the frame by frame, all right, if you slow it down, it's really easy to get the time for the free fall 2 places past the decimal. So that's how long, not how long the video was, but how long the free fall was. Okay, so last thing today, all right, see if you can get the height he jumped from. And also, let's throw this in there. How fast was he going when he hit the water? This is our last bit of notes and then a little work time for you.